So, good afternoon. I'm Krishna Kumar. Start with another episode of Analysis on RN, and it's a continuation of what we did in the episode 15, where we considered the problem of relating the derivative of a differentiable function with the partial derivatives. Now, we explore this connection further, and we shall just recall the definition of the of a differentiable function. So we have f from E, which is open, into Rn. Then what we say that f is differentiable at x belonging to E if there exists a linear transformation A from such that limit h tending to 0 of norm of zero. Now this is the definition of differentiability. If such a linear transformation exists, then we say that f is differentiable at x. So A is essentially an element of now in the last lecture we have connected f, the A, with the partial derivatives of f at the point x, and we found that this is what it turns out to be. The representation, if Bn and Bm are ordered linear spaces, ordered linear bases of Rn and Rm respectively, then the matrix representation of A with respect to is given by in terms of the partial derivatives of f at the point x. That is, you have d11 f1 etc. d1 f1 etc. dn f1 and so on. There are partial derivatives with respect to x1, x2, etc. xn. So you have d1 fm where difj is equal to dfj by dxn. Okay, I running from j see what you have is this, that x equal to xn e and f equal to so that f is a map from E to Rm. So this is what we have explored already. So once the function is differentiable, then all the partial derivatives exist, and then the partial derivatives give a representation for the linear transformation in terms of the standard basis. Now this is exactly what we have proved so far. Now the question that you ask is this: is the reverse connection true? Namely, if the function has all its partial derivatives, first partial derivatives, existing at a point, then does it imply the function is differentiable? Okay, so the question is, all the partial derivatives of x's of order x's then does it imply f is of course f1, f2, etc. These are the real valued component functions of the vector valued function f. X is of course the vector in E, right? So x1, x2, etc. So this is the question that you ask. So is the knowledge of the partial derivatives good enough to compute the derivative of the function? Because we know that if it is differentiable, then it can be done. That's what we have proved. But suppose you know that all these partial derivatives exist at a point x. Does it mean that the function is differentiable? Now to investigate this question, we will look at the example. So this is the fourth one that we are considering. F of xy is defined as x cube divided by x square plus y square not equal to 0, 0. And this is equal to 0 at now we can compute the partial derivative. Okay, one observes that f is defined from R2 to R. There's only one component for f, but two variables. So we have the following. So we write d1 f at 0, 0 we will calculate. This is equal to, one can easily compute this because what you do is you are working along you are freezing the function on the line y equal to 0. So this is essentially limit x tending to 0 of f of x. And this you can easily see that this is equal to what one gets is this. You are setting y equal to 0, therefore it is x cube by x square, so it is x. So x minus 1 divided by x, therefore this is equal to 1. Similarly, f d2f at 0, 0, this is equal to 0. That you can easily find out because you are now working along the y-axis and this is the point 0, 0. So you set x equal to 0 and then you see that the function is 0. Therefore, on this line the function is defined as 0 and therefore its derivative along that direction is also 0 at 0. So in particular at 0, 0 the derivative is 0. Therefore, if f is differentiable at 0, 0, then the representation for the of the derivative of x, you know, it is a with respect to the basis is given by the 2 by 2 matrix. So we remove that. We use this formula, therefore you get, this is actually a 1 by 2 matrix. Because it's a mapping from R2 to R. So it's a 1 by 2 matrix, and the 1 by 2 matrix is given by yeah, we will write it out, is one zero. It's a 1 by 2 . So you see that f derivative, suppose we take h, then what you have, f of this is equal to what you have as h cube, h1 cube square minus this part would give you simply h1. And if f is differentiable, this should be of the order of you know, a limit of this when divided by square root of h1 square plus h2 square, and let h1 and h2 go to 0, should be equal to 0. Okay. So this is what, so we investigate. H divided by zero. Is this equal to this? Is what we are exploring. Now choose H2. Then F derivative or 0 0 active over H divided by norm of H equal to limit H tending to 0 of what you have H1. We have already got this, so this is, you simplify this. Now this I can simplify and write it as H1 cube minus H1 cube 0. So this is H1 H2 square minus sign no sorry, okay, yeah. So H tends to 0 is corresponding to this is H tending to 0 . Therefore we look at this limit. What is norm of H? Norm of H is equal to, in that case it is mod H1. Therefore you get here, so we can now work out the limits. Therefore limit H tends to 0 of 1 upon norm H into this is equal to norm H is equal to mod H1. Therefore this is equal to you have mod H1 here, so you have in fact 1 by 2 this is not equal to 0. So that's the problem. Okay. Therefore, which implies so this is the conclusion. What does this mean? This means for our question, so even if, hence, we infer that even if the partial derivatives of f exists at x belonging to E, x may not be f x. So this is the conclusion that you have. Okay. So the existence of the partial derivatives do not imply that the function is differentiable at a point. That's a very interesting observation. Therefore, that of course leaves the question, then under what conditions on the partial derivatives one can infer that f is differentiable So what further knowledge is required? You know that if f is differentiable, certainly the partial derivatives exist. There is no problem about it. The existence of partial derivatives is a foregone conclusion. But then you ask, and you also know that the representation for, or the matrix representation of f derivative is given, can be given in terms of the partial derivatives with respect to the standard basis. So that's also taken for granted, and there is nothing, no doubt about it. The converse question that we have asked, and we have seen that mere existence of partial derivatives at a point does not imply the function is differentiable. When you ask the natural question, then what? Okay, if that is not the case, then what actually helps you to conclude that the function is differentiable? Now this is the question that you are asking now. So let me leave the question at this level and then come back to this, and then in the meanwhile we will look at another problem. Okay, and what we want to do is we want to see how the partial derivatives can be used to compute the derivative of a function in a particular direction. Okay, so suppose, so the next question is this. So we look at the example. So the question that you ask is this: what is the relation the directional derivative of a function and the partial derivatives? Whenever they exist. Okay, in this regard, we'll make some investigations. Okay, so what is the problem? The problem is you have a function defined from some e into Rn. It's a real into R, a real valued function is given. Okay, and then we find out the this is the question that you are asking. Okay, let's investigate this. First of all, the directional derivative exists. So we look at this problem. So we have, this is Rn and some open set or connected set is given in Rn. Now we define so this is copy of R1. So we define a map from here to R. Fx. So this function is given. Now we assume that this function is differentiable. Okay. Need not be, I mean, that be too heavy a assumption. So what we do is to compute the derivative in a particular direction. Suppose you want to find the derivative of this function in this direction. Then what do? You introduce a map from some interval of of R1 and define a map gamma from the interval AB to E. Gamma is differentiable. We assume gamma is differentiable. It's a map from gamma to R. Okay. So let assume gamma is differentiable so that gamma derivative T is defined as a map from on AB. Let please work the derivative at the point x0. Assume now you see that gamma has components gamma n because this is a part of Rn. So it's a vector valued function. So you have n real valued functions which form the component of gamma. And gamma T naught is equal to x naught. This is what we assume. And gamma derivative of T is defined. Therefore, gamma derivative of T is the tangent vector gamma. So it gives the tangent vector to gamma at T naught. Gamma is what I mean to say is this is the I am also calling this gamma, this curve gamma. So this is gamma A, gamma B. So this is gamma A. Essentially, you are imparting a kind of direction here. So there is a curve in space which can be considered as the path of a particle in space when you move from A to B in time. That's a sort of physical interpretation of the problem. And then gamma derivative in that case essentially gives you the velocity of the path of the movement at t equal to t naught. So every point on gamma you have the derivative giving you the tangent direction, and the this vector essentially corresponds to what is called the velocity. Okay. Now let us take the composition of these two functions. So you see that f composition gamma is a map from where and f is an intermediary to define this map. So let for t belonging to so if f is a continuous map or f is a differentiable map, then you see that f composition gamma is a differentiable map. Okay, therefore let us define, so if G is differentiable, then G derivative of t is a scalar, because you are talking about a function from one dimensional space to one dimensional space, and this is given by using the what is called the chain rule. This is actually two operators, one working on the other. So let us write down that. Then this is equal to, what is it, or even our usual differentiability tells you that if it is f derivative at gamma t acting over, see, look at this as an operator. Gamma derivative of t is an operator from R1 to Rn, and this is an operator from Rn to R1. Therefore, the what is it called, the operator, so this is an operator, that is f prime gamma t acting over gamma derivative of t is an operator from R1 to R. So this is for every t belonging to AB, provided of course all these derivatives do exist. Okay. In particular, at t naught, if G is differentiable, and at t naught G derivative at t naught this is the chain rule for these functions. Okay, that's clear. Now just for clarity, I'll write this gamma derivative of and the f derivative therefore R1, that is clear, and this gives okay. So we are now, what you are doing is you are restricting finding out the derivative in some direction. So if you want to find the derivative of f in some direction, then what you do is you introduce a curve in space whose derivative at the point where you want to evaluate and the direction in which you want to evaluate has the property that gamma derivative is, that is the tangent to the curve, coincides with the direction in which you want to compute the derivative. Okay. Now let us also look at this, put this in the this one. So this is what we obtain. Okay, now what one finds is this. Suppose we introduce standard basis. Then we have f derivative at gamma t naught is given by the matrix this is what we have. This is the matrix representation that you get. And what you have is this. Gamma derivative at t naught is given by, let us write it as a column vector. We want to write this operator. This is equal to this is the dot product of these two essentially, given by sigma okay. Now this is the change. So you have g derivative computed, and what is g derivative? G derivative is the rate of change of f along the path gamma. Okay, right? The rate of change of f along the path gamma. So we are just isolating and trying to find out the derivative of the rate of change of f along a particular path in G. Okay, so G is the rate of change of as an abuse of notation, gamma is the map that we have defined, and we choose to designate okay, so we are using the same notation. So that is something which we look at. So that is the geometry of the whole thing that is happening. Now what we want to do is we want to do more. Okay. In fact, what we want is, now we have introduced a curve gamma, and therefore we have fixed the direction along which we want to calculate the derivative of f. Okay. Suppose we want to calculate the derivative of f along all possible directions at a given point in R. So now what we want to investigate is this. F along all possible directions at a given point belonging to E. Is it possible to use the partial derivatives? This is the question that you are asking. You know that if the function is differentiable, then all the partial derivatives exist. Even otherwise, the partial derivatives may exist. Okay, right. But the function may not be differentiable. Partial derivatives may exist, but the function may not be differentiable at a point. Now this gives a more general formulation. So what we do is, see, look at this vector, f derivative, okay. Let us define each x belonging to E. We define the gradient of at x by the following. It is denoted by grad f, which you are familiar with. It's a vector defined by EI, where of course EI is So what one has is the following. This is E. Now you are giving a map from E to it's a real value. Okay. So what we have is R. It's a real number. Now you observe that the grad f you have defined. The grad f you have defines a vector. We shall assume is not equal to 0. This is our definition. So we assume this is true. That means there is that is grad f determines a well-defined direction for the given f. And this is a vector, well-defined direction that x belongs to. Okay, and that is non-zero. That's the assumption that we are making. Now, what one does is suppose you choose assume gamma is differentiable. Gamma t x and now you see gamma has components, so gamma t is equal to and you have gamma derivative of t equal to here. That is the meaning of this. Okay. Therefore, what do we have? G derivative of t, if g is equal to the composition of gamma from R, then g derivative of t is given by grad f at gamma t dot, what is it, gamma t. So this is something that we have written what this is. Okay, yeah. Where of course grad f at gamma t this is equal to sigma I equal to 1 to n di pi. That is the gradient of f at gamma t. Now this is what we call so what you are doing is this: once the function f is given, you are associating with a vector. Okay, this is a real valued function defined on E, that is a function of the n variables x1, x2, etc., xn. We are associating with that a vector called the grad f at each point. So corresponding to, once it's a differentiable function, and you see that at each point there is a vector. So there is a vector field in this space. There is a vector field in this space. Now a lot of nice geometry follow. Okay. So what we want is, we have grad f giving you some information or all the information of the change of f in all possible directions. Okay, that's what we are doing here, right? So if you want to get the change in one direction, now we will see how it really comes. Okay, so what we want to say is that grad f at x is a vector associated with f at P, which contains all information about the derivative What do I mean by that? So if you want to know the change of f along a particular direction, you introduce a curve whose derivative at that point is given by gamma derivative, and then what you do is you take this, take the dot product, evaluate this at the point gamma t, and then take the dot product with gamma derivative. So that gives you the rate of change of f along that direction. Okay, that's what we mean by it. So let us write down that. Okay, what is the geometry of this? We will investigate. So what I mean to say is this. So grad f, which is a vector, if you write down the components of this vector, this is actually and we are also assuming that grad f is not equal to 0. That means all components of f is not equal to 0 at any point. It's our assumption. That is, given f from E to R differentiable in E, grad f defines a direction field this is E and f is given R, then you see that at each point so you have a direction field here. This is the gradient field. In physical problems, this has a meaning. Okay, this takes the meaning. So this direction field actually gives you all information about the directional derivatives. Okay, because all that you want is, if you want to get a, suppose you take this point and you have a direction u, a vector u, then suppose you want to calculate the rate of change of f along the direction u, to take grad f dot . Okay, so that's what we have. So it is something like a velocity field that you have. Let me give a definite meaning to this. Okay, let us take an example, a specific. Assume defined by f of x2 square. So what are the equipotential curves? I'm using the word potential suddenly brought in here. So this f is often interpreted in physics as a potential function. It's so the field that is available appears as a gradient of a potential function. I mean, that's the assumption. I am not going into the details of that, but those who have done physics would understand the meaning of that. So what are the equipotential curves? That means it takes the curves along which it takes the same value. So this is the one axis, this is the two axis. Now you see, what we want is looking at this curves x1, x2 equal to constant. Okay, so when C is positive, you see that they are, in this case, concentric circles. So these are say x1 square plus x2 square equal to C, where C is some positive number. So all these points map to the same point in R. Okay. So this entire set of points, so if I call this circle C, write R. Let me write R, the circle with radius R, then CR equal to, we are taking R positive. Now along CR you see that F takes the same value. Therefore, if you were to walk along this curve, move along this curve, then you see that there you don't feel any change of F. It is the same potential that you have. Whereas if you move in some other direction, then you go into another curve and there the F changes, or the what you call the potential changes. Okay, and you see that the direction grad F is orthogonal to the equipotential surfaces. Why? Because if you take any vector along this, then you see that the grad F is orthogonal to it, and the dot product would be vanishing because the value of the function does not change along this direction. So throughout the curve you have the same value, therefore it does not change at all, therefore the derivative is going to be 0. And grad F, it turns out to be orthogonal to the equipotential surface for some value. Okay, right? So that's an interpretation that you have. So the direction of, so, and you see that F undergoes maximum change along grad f. Okay, so I will come back to this point. That's quite easy to see, because in the tangent direction the max f undergoes no change at all, whereas in the normal direction f undergoes maximum change. In any other direction it's a different, at each direction it undergoes a certain change, but that change can be calculated. Therefore the derivative or the change of f, okay, in this region can be computed if you know grad f at each point. Okay, or what you call the rate of change of in any direction, or I will write the rate of change. So grad f carries two informations. There is a magnitude as well as there is a direction. So it's a vector field that you have. So this is the vector field. In some cases it becomes the velocity field. And one can measure the rate of change along in a direction by simply projecting it along this. So you take grad f dot u hat. That will give you the rate of change of f in the direction u. Okay, so let me formulate this. Let me quickly get through this now. I think there is very interesting, fascinating geometry associated with it. So we take Rn, it's a vector in Rn, and with the norm u, that is, it's a unit vector in Rn. So u is not equal to 0. And choose gamma t to be equal to so it's a linear direction that you have. So you have this line given by Then what you have? Then gamma derivative of t, it's a vector for everything. It's a constant direction that it's the slope of this line that you have. Okay. Then you have, see, G0, GT you define as then G0 is equal to f of gamma 0 and this is equal to f of. Now let us compute this. So you see that G derivative at 0 is essentially grad f x dot u. That's quite easy to see from our discussions. Okay. So what you have is that G dash t is so at dot the vector, this so you get it. This limit is usually called the directional derivative of f along u at. So once you get the gradient of f, the potential function, then you get a field, and this field usually determines all these information. Okay. So if u is equal to ei, then what we have is this. We denote by the directional derivative d u f at is essentially ui. This is the directional derivative that you have. Okay. So one can get the directional derivative once you know the derivative, the partial derivatives. So one can function if we know the directional derivative, the partial derivatives of provided f is differentiable so this is the information that we have. Okay. Yeah. I think that's a nice place to stop. And then we take up now a question. Suppose you know that f derivative is equal to 0 in a whole region E. What can you say about the function? Now we can conclude that f is a constant. Okay. So this is one of the generalizations that we are going to get, because we know that when you take a differentiable function on an interval, a real value differentiable function on an interval AB, and if you know that the derivative of the function vanishes at every point, then we know that the function is necessarily a constant. You are asking the following question: is this true in general? Okay. Suppose we know a function f is from Rn to R is differentiable, and we know that f derivative is 0 at every point. Does it imply that the function is a constant? Now this question we will take it up in our next talk. Thank you very much.